The last bit that we're going to look at is redox reactions. We're going to look at identifying them first, because sometimes we're not really sure whether something counts as redox, reduction and oxidation. Remember that anything that involves oxidation, if it's a full equation, will also involve reduction. It's just sometimes we refer to particular things as oxidation or reduction, and we kind of miss out the other half that's going on. For example, this reaction is definitely oxidation because the hydrogen is gaining oxygen. So the hydrogen is being oxidized to make water. It's also reduction though, so the oxygen is being reduced. And it's also combustion. So anything where you've got a reaction with oxygen must be a redox reaction. We can have the same thing with a metal. So magnesium and oxygen, that's definitely a redox reaction. We may call it oxidation because the magnesium is being oxidized, but the oxygen is being reduced because it's gaining electrons to make magnesium oxide. And then slightly less obvious, but we can see that in this reaction the iron starts off with oxygen attached and then loses it, and so the iron is being reduced because it's lost oxygen, and the carbon monoxide has gained oxygen to become carbon dioxide. So those are fairly obvious redox reactions because they all contain oxygen. So we can see that oxygen is being moved around in some way, then it must be redox. What about some slightly more complicated or things where there's oxygen well in virtually everything? Is this a redox reaction or not? Well, it's not, because what it actually is an acid-base reaction. And there is another hint for identifying redox reactions, is that normally in a redox reaction you either end up with an element that turns into a compound, or a compound that becomes an element, or you get both, and that's very likely that you will have both happen. So in this case, everything's staying in a compound. There's not really any change. All that's happened is the copper has swapped places with the hydrogen. Swapping places like that, where they both end up in a compound, is not redox. That is an acid-base reaction. So all that's happened is the hydrogen has gone with the oxygen to make water, the ones we were just talking about. Okay, what about the next one? Well, look, I told you to look for elements going into compounds and compounds going into elements. So yeah, this is definitely redox. Magnesium starts as an element, ends in a compound. We'll look in a moment at the half equations so we can see what happens in terms of electrons, why that is a redox reaction. Next example, not a displacement reaction technically. Copper oxide is reacting with hydrogen, well, hydrogen is an element, to make copper and water. So copper now becomes an element when it was a compound. Also copper has lost oxygen, so that is definitely a redox reaction. Next one, magnesium and acid. So we didn't cover this in the acid-base reactions because magnesium is not a base. And we're not making water, so it's not quite the same as a standard neutralization like the top one. So what is happening though is that magnesium starts as an element and ends as a compound. To do that, it must have lost electrons to make magnesium ions. And then meanwhile the hydrogen starts as hydrogen ions in the acid and becomes an element, hydrogen gas. So it must have gained electrons to go from H+ in the acid to hydrogen molecules. So that is a redox reaction. Two, we don't always call it a redox reaction at GCSE, but it definitely is. Look at the bottom one, a little bit trickier, but everything's in compounds. So this is decomposition of a carbonate. Everything in compounds like that, certainly at GCSE level, that is a sure sign that there is no redox going on, and when you move on to A level you'll look at new ways of actually determining if everything is in a compound state, why it's not redox. But just stick for now that decomposition, whether you're breaking it down into two separate compounds from an original compound, also cracking, that is not a redox reaction. Okay, we're also going to look at displacement, And with displacement, we can then look at how we do ionic and half equations for redox. So that example that we just looked at, copper sulfate plus magnesium, making magnesium sulfate plus copper. Classic metal displacement reaction. Happens because magnesium is more reactive than copper, so it displaces it. In the ionic equation, therefore, what did we get rid of? Well, we said that magnesium displaced copper, and we never said anything about the sulfate. So this is not quite the same as our precipitation. What we're now focusing on is, instead of looking at changes of state, we're looking at the changes in charge. And a change in charge happens if you go from being an element to being in a compound, or the other way around. Because metals in compounds have charges, and metals that are elements do not have that ionic charge, because it doesn't make sense to say that a lump of magnesium all has like a 2+ charge. Can't lose its electrons if there's nothing to give them to. So we get rid of the sulfate ions, cross them out. Just like before, if we're getting rid of them, we're going to leave a charge in its place. So the Cu that was in CuSO4 we write now as Cu2+. I'm not worried about state symbols for redox reactions at the moment. The magnesium was always just magnesium on its own. So just because it says ionic equation, you don't have to have everything have ion charges on it. And then we got rid of the sulfate, which means the magnesium left behind has a 2+. So we're just swapping round. Cu2+ becomes Cu, Mg becomes Mg2+. So we can write half equations to show the two separate processes. The copper going from 2+ to Cu, and the magnesium going to Mg2+. So here's my copper 2+, and I've just taken the copper part out of the ionic equation. So it starts in a compound with an ionic charge, and it ends as an element with no ionic charge. So what is not balanced here are the electrons. Well, how do I go from being 2+ charge to having no charge? I can only add electrons. Electrons have a negative charge. So how I get from a copper ion to copper is I'd have to put the 2 electrons back, and we write them with an E and a little minus charge there. 2+ plus 2 minus gives me no charge, and the one on the right has no charge. So I'm balancing the pluses and the minuses, and I can only add minuses. And then with my magnesium, magnesium starts as an element. I think this one is easier to understand. It ends as Mg2+, so therefore it loses 2 electrons. So they go on the right-hand side because, again, 2+ plus 2 minus gives me overall no charge, and over there I have no charge either. So my charges are balanced in both of those. The other example of displacement reactions is with the halogens in group 7. So here would be a full equation for the reaction of sodium bromide with chlorine to make sodium chloride and bromine. And this happens because chlorine is more reactive than bromine, so it displaces it. So writing an ionic equation, the thing that's not doing anything is the sodium. The sodium starts in a compound. It would have a charge of Na+, because that's an ionic compound, and it ends also in an ionic compound. So again, we're not looking at changes of state like we did with precipitation. We're looking at changes in charge, which happens when it goes from being an element to a compound. So I can get rid of my sodiums from sodium bromide and sodium chloride. One thing to notice is I still need the balancing in an ionic equation. So the 2 is still there because I'm going to make Br2 at the end of the reaction. So I'm going to need 2 bromide ions to do that. And the 2 in front of the chloride ion because I start with Cl2. Can you use halves? Absolutely you can. It's less common and it's less necessary that you know how to use halves for this sort of reaction. So writing the half equations, I'm going to take the bromine on its own. What's happening to the bromine? Starts as Br minus, ends as Br2. So we've got to be a little bit careful. We can only add negative things. We can only add electrons. I can't add minuses on the left because the left already has a minus charge. So I'm going to need to add them on the right hand side. So it's not that I'm trying to make both sides equal 0. Sometimes they do, but sometimes they don't. I'm just trying to make both sides equal the same charge. So I need to add electrons on the right. And because it's 2 Br minus, it's 2 electrons. So each negative bromide ion, imagine it was 7 in its outer shell and that one extra one, each one loses 1 electron to make 2E minus. Chlorine, this time it's gaining electrons, so it starts with no charge and it ends up as 2 chloride ions. And so on the left hand side, because it's gaining electrons, I'm going to be writing 2E minus. So 2 minuses on the left, 2 minuses on the right. If you wanted to try and imagine what was happening here, then imagine that you had your chlorine molecules. This is very bad drawing with this stylus, I apologise. And they are sharing electrons in a covalent bond in the form of Cl2. And I'm very gently trying to draw my 7 electrons. So each chlorine's got 7 electrons, sharing one in the middle to make 8. We then add another 2 electrons so that each of my chlorines has the 7 electrons that it started with, and then we broke the bond, but we broke it by adding another one, and that's what gets us our chloride ion, which looks like that. And that's why there are 2 of them, but you can see that I needed to add 2 more electrons because once I pull these apart, they each only have 7.